Hello, I'm Ed Wicklein with Corello Engineers. I'm here today to talk with you about CFD modeling of chlorine contact basin baffle factors. This work is in support of developing a technical guidance manual for the Colorado Department of Public Health and Environment. We've put together a number of modules to support the guidance document. This is the first one, CFD Modeling Overview and Workflow. As mentioned, I'm Ed Wicklein with Corello Engineers. So, CFD modeling of chlorine contact basins. We're going to try and answer a number of questions on this talk. What is CFD modeling? CFD modeling workflow, the modeling tools that are available to us, how to build quality models, and model results. So, computational fluid dynamics modeling is an engineering tool for evaluating fluid flows. It captures three-dimensional fluid conditions. It includes turbulent fluid motion. You can incorporate multi-phase physics within the model. You can simulate energy, reactions, and of course, it's all aided by high-end visualization software to see what's going on inside, which is why it's otherwise known as color fluid dynamics. So CFD modeling starts with the fundamental equations of fluid flow, the continuity equation, the momentum equation, and of course, we need some sort of equation to capture the turbulent effects that are going on in there. This is unknown. A computational mesh is developed of a given domain that you'd like to know what the fluid conditions are within, and then through iterative methods, it's solved, yielding our results. In this case, it'd be a section of a pipe, and the contours would be representative for perhaps velocity levels or turbulence or another constituent of interest. And the vector arrows show the direction that the flow is going. The benefits of using a CFD model to determine the baffle factor are many. The model can be done during design, which will reduce uncertainty. Obviously, if you haven't built the tank, you can't go conduct a physical test, which was the more traditional method of evaluating factors. You can easily identify sources of inefficiency to create better designs. In the example on the right, we looked at 5 different options for Aurora, Colorado at their Wemlinger plant, and find that with the same basin, we get a whole range of baffle factors or hydraulic efficiency through the system, depending on the ultimate geometry that's selected. Other advantages include there's no disruption to operations. When you run a test, you do want to hold the flow rate steady for the duration of the test, which could be disruptive to customers. You're not limited in the flows that you can test. The numerical model can obviously run any flow regardless of what the plant can produce or the system can absorb. And it's pretty easy to evaluate very complex systems where it might not be so easy to conduct a tracer test. So there are some challenges in CFD modeling with baffle factors. Number one, how do we ensure it's right, which is the overarching purpose of the guidance document. The computer is perfectly capable of developing wrong solutions that perhaps look correct due to the colors. So we're going to try and get through some of these issues today. You need a sufficient domain to capture the problem. You need a high quality computational mesh. You need to use the correct numerical methods for your approach. You need to use verified and validated CFD codes, and you need adequate convergence of your solution. So basic CFD workflow for CFD modeling, we define our objective. In this case, it's the baffle factor of a chlorine contact basin. What goes into that's the geometry, the flow, operating conditions. Then the model is built, you develop a computational mesh, simulate the hydraulics, following solution of the hydraulics, simulate a tracer. From that tracer, you monitor at the outlet through the solution, and you can determine the baffle factor from that, and then you develop a report to document it all. The more complete workflow includes a number of loops in the middle to make sure that you've got a very high quality mesh. There's a number of quality checks that need to be done, and then the mesh also needs to go through an independence check to verify that you have sufficiently resolved the domain you're trying to solve. So there's a number of software tools that go into this process. They can be integrated or discrete. There's some packages where every piece of it's integrated into a single piece of software, some where you have the option of using different packages. You need a mesher to generate the computational mesh, and there's many choices available for this that all provide you the tools to ensure you have a high quality mesh. A key piece is the solver, the actual CFD code that solves the fluid equations. There's many out there, but it needs to be a well-validated package. Commercial examples would be Fluent, CFX, CCM+, and Flow3D. And then, of course, there's open source software such as OpenFOAM. We would recommend sticking with these codes given their extensive validation and numerous peer-reviewed journal publications demonstrating their ability to simulate baffle factors in contact basins. And then once the problem is solved, we need a visualization software to evaluate the data and develop our figures. The examples on the right would be differences between a commercial software. On top is ANSYS Fluent, and there's numerous pieces that you can monitor your solution while it's running. Open source software tends to be run more from a script, and it may be a little bit harder to monitor the solution, but it does still provide excellent results. So to do the CFD modeling, we need to start with the geometry. It's created from somewhere, either a CAD package or within the meshing software. It needs to be come from either a designed facility or a built facility. And then we need to figure out how we're going to manage the water level, whether it's a free surface model or rigid lid. Generally, contact basins are rigid lid. They operate at a fixed level. If they were free surface and the level were changing through the solution, then our hydraulic residence time would become a variable. So then the mesh is built from the geometry, and the top left shows the process of decomposing it. The mesh needs to be well defined in different areas to make sure that you have a quality mesh, and so the overall fluid volume will often be cut up, or individual surfaces or faces may have mesh parameters assigned to them to control their size. The lower left would be the mesh geometry, and you would go through quality checks at this point. Here we're looking at the skewness of the mesh, how distorted it is. And so there's a number of checks we'll talk about in a few minutes that we need to cover. Following the meshing, you simulate the hydraulics, and the convergence needs to be monitored. On the top image is the average of global residual. So you're solving the equations iteratively, and it's a difference between progressive steps. As the number decays, your solution is converging on a set value. Other monitors would include point velocities or other areas of interest. Here we've got curves plotted as the solution iterates of velocity at a couple points of interest in the domain. We can see that the red line is pretty stable. The velocity is not fluctuating at that location. The black line indicates it's in an area where there's some instability. And so as it iterates, it is converging on an average solution at that location. And so we need to make sure that, if, for example, we stopped at 500 iterations, we'd have a very different solution than anything after 2500 case. We need to make sure that the mesh resolution is good, that we have enough cells to solve the problem we're looking at. And so mesh sensitivity test is typically performed for problems that have risk, such as baffle factors, which directly apply to public health. So here we've extracted a number of data points from the converged solution at a bend where there's some instability in the flow, a point where we think the model might have uncertainty. And we compare progressive refinement of mesh. So we start with, for instance, 10 cells across the width, 20 cells, 30 cells, and we compare this coarse, medium, and fine mesh to verify that the velocity is unchanging between these solutions. And what we see is that the R squared is 0.95 between the coarse and the medium, so it's probably pretty good. The two meshes produce a very similar solution. And further refinement from the medium to the fine, we've increased the cell count significantly, increasing the computational overhead, and yet our solution hasn't changed that much more, taking that next step. And so we would conclude from this that with the R squared of 0.98 between the medium and the fine, that our medium mesh is probably sufficient for a given solution. After mesh independence, we run the scenarios we are interested in for the given problem, calculate the flow field first for a chlorine contact basin, which we see on the left. The solution here is stabilized and converged. Following that, we run a tracer test where we release tracer at the inlet, track it through the domain for at least a hydraulic residence time, monitoring it at the outlet. So here's an animation. We've done a slug dose test, tracer's introduced, and it travels through the tank and flushes out. You can see areas where it holds up, where it's short circuiting in that central region of the tank, where it's taking a long time for all of the tracer to exit. As we monitor at the outlet, we plot our curve of normalized time versus outlet fraction. And from this, when 10% of the tracers exit the domain, we would define that as our T10, or our baffle factor for the tank. And with that, we've stepped through the basics of developing a CFD model. Thank you. I'm available to answer questions if you have them later, or there will be a live session that will have a series of questions answered, which hopefully will get recorded. Thank you.